Let's continue. So some people have asked me if the slides are going to be posted online. Yes, they will. The PDF will be available on the BIOS website. And I'm going to follow Zan's advice, and I'm going to talk a little bit more about the force field format. I must repeat, I want to tell you guys that this information is also in the NAMD tutorial, and it's well explained there. As a matter of fact, this is the NAMD tutorial that we're looking at right here. So this is for SHARM22 with CMAP correction. And well, whenever this is an old charm input file, whenever you see an exclamation sign, that means it's a comment. So the first part.
Control plus plus.
Sorry?
It's really small. Can you hit?
Oh, yeah. Is it too small?
Thank you.
That's better? I'm sorry, I'm too close. Okay, so okay, here, SHARM22, and this is the CMAP version, okay? So you have the authors here. So here's the first thing that comes in the, okay, so something that we're gonna examine here, this is the topology file, not the parameter file. So this is when you run PSFGen, like, I don't know how many of you guys did the NAMD tutorial, but you have the topology entry in PSFGen. This is what you're loading when you issue that command. And what you're reading is this file here. So the first thing that the topology file defines is the masses. And it starts with this mass, 4-letter code here. This is just an index number, and this is the atom type. So as you can guess, all of these are hydrogens, right? But depending on which, for instance, this guy here is a hydrogen for a tip 3s3p for that model of water. This is a polar hydrogen. This is an N-termini hydrogen, and so on. So you have the atom type, but they're all hydrogens, and they all have the same mass. Same for carbons here. Okay, so these are declaring the. This is just declaring the atoms that are going to be connected. We can skip this up. Let's look at an entry for a residue. So once you have defined the atom in the mass section, you can actually start defining a residue. So a residue is actually, if you look at this number here, is the total mass, the total charge of a particular residue. Yes?
Just to back up 1 second. The topology file is used by PSFGen
Yeah.
to generate the PSF file from the.
That is correct, yes. So you never use the topology file during the simulation. You only use the topology file to prepare the files. That is correct. So so the total charge of an alanine is 0. It's not charged. So you have the N-terminal of the alanine. You have the C-terminal of alanine. And what we have on this field here are the partial charges. So can someone tell me why do you think we have this group here? What is special to the atoms within a group?
Well, they have probably something charged 0.
That's correct, yes. So if you sum the charges of each group, is actually 0. So the groups have neutral mass, neutral charge here.
So how would the group?
Sorry?
How a group is considered?
A group is a partition scheme. So for instance, this is a methyl group right at the end, right? That's actually the side chain here. So if you sum the total charge of that side chain is 0. This is the backbone. If you actually sum the charges of the backbone there, it's also 0.
How do you get
So that's done, that's a parameterization, and that's done using ab initio quantum mechanics calculations. Yeah, so,
They also use, I guess, experimental data to train for.
Very rarely,
Oh,
yeah.
What's the amount of charge used
Those are for,
Because I know sometimes it's 1 for the charged amino acids and 0 for the non-charged. But I mean, what does NAV actually use that number for?
which number, sorry, which number?
I mean, the atomic partial charges are used in calculating the coulombic term. Well, what's the amino acid charge used for? It's a number.
Oh, that's just a check. That's not used for, yeah. So that's, yeah.
What's the meaning of partial charge? Is it the effective charge?
So each atom is assigned a charge. The total charge of this group is 0, right? So the partial charges are restrained, are assigned in such a way that the total charge is 0. So you have a partial charge, for instance, for the carbon, for this CV here, you have a minus 0.27. And for the hydrogens, you have a slightly partial charge, a slightly positively partial charge. They're called partial because they're not integers.
Right. The effective charge is subtracted from some kind of value. They might consider something like an isolated atom charge, but not exactly, but there's some values.
Takes into account the separation of charge in a molecule.
In a fractional way.
But those are the partial charges that go into the electrostatic term.
Yeah, those are the ones that are calculated in the Coulomb, in that Coulomb term.
And getting that whole bunch of information, that's a major industry. That this guy McRell does, along with Benoit, who's one of the guys who developed the Drew parameterization. And they periodically update these. And if you use charges and from Amber, they're going to be different because they do the quantum chemistry calculation to get the partial charges slightly differently than the charm lock together. Right? So each of those groups has their own way of doing it, and that's why you cannot borrow back and forth from these guys.
Mm-hmm.
So is there just generally one topology file that you use for most proteins?
So,
Compare the PSF?
so for for charm 36, there is only one file for 22. Except if you have like special residues that have been parameterized. If you want to use CG and FF, you have the topology files for those other components. So there are at this point in time, charm used to be a mess. Used to be like everything in a single file. So it's evolved in a way that is now split into multiple files, including like you have a file for carbohydrates, you have a file for nucleic acids, one file for proteins, and one file for special residues like phosphorylated residues and things like that. So yeah, but these partial charges, as they were commenting, this is what goes into the Coulomb term in the potential energy function. So this is what defines the connectivity between different parts. So like for instance, for an alanine, we are defining a bond between CV and CA. We're defining so these, for instance, this bond, you read it pairwise. So this is defining CV, CA, N and HN, N and CA. And this bond is what determines the actual topology of a residue, for instance. You have the field double, but it's more of an alias. It doesn't really mean anything. It's the same as a bond. It means they're bonded. There is no difference between double bonds and single bonds in charm. The improper angles are, they take 4 atoms. So you can see these are 1, 2, 3, 4, 1, 2, 3, 4. So these are defining 2 improper. Impropers is what adjust the planarity of the residues. These are the CMAP terms, which is the CMAP correction, which is unique to charm 22. These are, if at some point the force field people try to have explicit hydrogen bonds, it was kind of a mistake. There are no one uses explicit hydrogen bonds, but at some point you will have these entries that will explicitly define a hydrogen bond. No one uses that anymore. This is where the magic happens, where I like the most, the internal coordinates, because when you do, for the people here who did the PSF Gen tutorial, I don't know if you guys play with guess coords. Like it actually guesses the coordinates of any atoms you might be missing. So what he actually uses is the internal coordinates. So these internal coordinates, so for instance, if you're missing a C alpha, he can use the internal coordinates to place that C alpha if you're actually missing the coordinates. So these are the IC. These are actually known as the IC tables. This is also in the topology file. So actually, a common mistake people have is they think because they have a topology file, they can use guess coord to assign the position of the atoms. That's not always the case. If you don't have the IC tables, there is no way the PSFGen can assign the coordinates to those unknown atoms. Is that okay?
So does that specify the relative location? Of
Yes,
the
yeah, they're just internal coordinates. No?
And what are the units of those numbers?
These depend, like some of them are distances, some of them, so you actually define distance, angles, yeah.
So the distances, is everything in
Armstrongs, yeah. So the units in charm are, actually I forgot. I'll have to owe you that, but it's a very, it's Armstrong.
Armstrong and angle, so it's like bond angle and
Yeah, but I can't remember, but it's A something, MK something. I'm sorry, I can't remember it from the top of my head. But the units in the charm force field are always, for distance, are always Armstrong. That's what I meant to say. So you guys, I mean, for you guys who did the tutorial on, you guys didn't do the QuickMD tutorial, but did the old NAMD tutorial or VMD tutorial, you probably apply patches, or like the first enter, last enter for the N-termini. So in principle, when you first build the molecule, the molecule is just like have these, doesn't have the what we call the patches, which is you have, like for instance, the N-terminal patch and the C-terminal patch. And you have other series of patches, like if you want to build a disulfide bridge, you can apply a patch. And that's also contained in the topology file. So any patch that you apply, like for instance, if you want to mutate, like not really mutate, like if a glutamate is a protonated glutamate, you actually apply a patch. So you first assign a glutamate, and then you patch the glutamate with a protonated glutamate. And then you can do guess coord so that extra hydrogen is assigned using the internal coordinates. But I think what's important here is you need to realize that the topology file contains a lot of information. As I said before, it's a database. And as Zan was pointing out, this has been the work of Alex McCarroll, Benoit Roux, and other people for, I don't know, 30 years. So it's a very big effort. These are more of the same. Let me see if there's anything else that we can. I mean, you can just look this in the tutorial. Is in the NAMD tutorial that some of you guys worked last time. So there is. So we talked briefly before about the tip tree water, which is the water commonly used, and maybe the commonly used with the charm force field. So as you can say, it's your typical water, contains 1 oxygen and 2 hydrogens. Nothing strange. But it's a 3-point particle. That's what the 3 stands for. There are more sophisticated water molecule models with like 4-point particles and things like this. In fact, the Drude force field uses a 4-point water model, which is different from the tip tree water model. But it's the same as a neutral water. You have you don't have any sort of patches at the beginning and at the end, and the ions, like sodium and chloride, they just look like this. They have a charge assigned, like in the case of sodium, a positive charge, and in the case of chloride, a negative charge. So something that is missing from this tutorial, I don't know if I have the latest version, so there has been this debate in the field, and there has been these corrections to the force field, how, like for instance, ions interact with carboxylic groups. Like for instance, there are different ways that these issues have been overcome, and those are common. They are now called the NB fixes. They stand for non-bonded fixes, and what they have. Some people don't like them. They say like these are like the force field should be robust enough that you don't have to use such tricks. But what it effectively does is it changes the electrostatic interactions between some ions and some other particular side chains, or particularly carboxylic groups. This has been kind of recent. The first report on this issue was, I believe, 2011. They had been updates in 2013 to the NB fix fields, the latest MBFX field came out this year. So if you're not using Charm36 released this year, you are probably using the wrong or outdated ion parameters. So there is, I guess there are two messages. Is like you cannot really stick to the old force fields. It's an active field, and things as simple as ions, we are still like converging to a better understanding. Now the Drude force field also has NV fixes. I mean, you probably know this since you work with Marcos. There has been this debate between, we've been talking Marcos, Benoit, Alex, and I. We've been discussing the interactions between Drude ions and the carboxylic side chains because it seems it's coordinating more ions than it should. And so we're like, it's actually a big issue because something that we're seeing is that you can actually start growing crystals on the surface of the protein. It's because you're coordinating more ions and you just essentially have a nucleation seed that you start growing a salt. Yes?
I think the brute force model could reveal also new interactions for molecules that are already stable in the conventional water because we found a new interaction for unstable right? Or molecule.
Yeah.
So if I were to use a brute force model with a regular already stable protein, can I also find new interactions? Or?
So that's hard to say, but so the current thinking on Drude force field is it's more computationally expensive, right? So, and many people argue that you don't learn a lot more from it. So I guess it's a case-specific situation. So if it really depends, you should look, that's what I do is I look with the classical force field first, and if the scientific question that I'm trying to answer is within the reach of a classical force field, then I just stick to the classical force field. And then if I see something strange going on, like as I was showing before with the cyclophilling A and the CA interactions, then I start exploring. The first thing I blame, first you check your simulation, first you check your structure and everything. Then when you rule out everything, then you start blaming the force field. But you have to have an understanding. Then when you have an understanding of something that it's already observed, like in our case was a crystal structure that wasn't stable in the simulation, then you can start make predictions. Yeah.
Can you say something about the scope of the nature of the changes between the Charm 36
and 22?
Yeah.
So, I'm not a force field expert, but I can tell you from the outside. So the 36, they recalculated all the charges, and then they also they have more experimental input. They also try to match some experimental observables, essentially. Can tell you from the lipid side, they reparameterize all the lipids. The lipids didn't used to have this van der Waals switch. They now have this van der Waals switch, and what it was that you would end up with the wrong surface tension of a lipid. So that was with the Charm 27 set of lipids. With Charm 36, you reproduce the lateral, like the surface tension of a lipid more accurately. It came at a cost that you essentially have to, you cannot really prepare a system with C27 and then run it with C36. You actually have to start all the way, and actually you should never do that. You should never prepare your system with C22, C27, and then run it with C36. You should start from C36. Because charges, they change charges, and maybe San knows more about this than she's more experienced than I am, but they update charges very often. So, and just because it is the latest force field, it also doesn't mean it's the best. So you have to be critical on what your goal is. There's also the D Shaw force field, right? The Charm 22 star, which is that's what is used in Anton simulations to fold proteins because it has a higher convergence rate. It has a problem that is when you try to reproduce the vibrational motions of the protein, something we will observe in NMR, it doesn't reproduce those well. So it can fold proteins, but the dynamics are wrong. So force fields are you have to be careful, and you need to know what kind of question you're asking to pick the right force field. There's also, I heard that someone was asking about the sugars, the glycans. I don't know who it was, but glycans are also an active field of research in terms of force fields, and it's there is obviously we cannot have our science is as good as our force fields are, unless you do like ab initio or things like that. But okay, are there any other questions? I mean, feel free to. This is more of a discussion than just me showing stuff because.
Is there a news site for force fields?
So for the charm force field, you can go to Alex McCarroll website. The thing there is if you download the Alex McCarroll's force field, it will only work in charm. So the best way to get the latest force fields that will work in NAMD and VMD is actually through the charm GUI, because they have if you have your own homebrew scripts. I mean, it's really just a matter of breaking the topology and the parameter file into two, because the way that Alex releases the force field is a single file, which is called top-par, and it's because Charm read this like as a computer code, and there is a big if there. So like if this was loaded as a topology file, skip here. If this was loaded as a parameter file, read this. So all the Charm GUI people do is they split the top part into two files. So that's the best source is Alex McCarroll website. The second best source is the Charm GUI. And they work actively with Alex, so that's actually the good thing. For the Druid force field, also the best source is, I would say, is the Charm GUI, because they get all the information from Benoit Roux and Alex McCarroll, and then they also give you when you use the Druid prepper, you also get the NAMD input files that you can then modify. So I think it's we're getting there with I guess the QuickMD is hopefully going to do at least from our side incorporate the latest force field and incorporate and make all of these easy for people, so you can just load Alex's force field and don't have to go through the Charm GUI step. But at this point in time, I think you're better off if you get it from the Charm GUI people. But yeah, it's active, so it's perhaps the end user doesn't have to worry too much. But it's good to keep an eye on it if you see anything strange. Are there any other questions? Okay. Let's get back. Oh no, not this one. Let's do this one here. Okay, since we look at the topology files, then we can retake from where we left before coffee break, which is the PSF file. As we just talked about, you use the topology files to generate the PSF file. This PSF stands for protein structure file. Here is a little, so for those of you guys who plan at some point to run big simulations, PSF also has limitation in size. You cannot run anything larger than 99999. Like that's a 10 million atom system. So that's your PSF limit. Once you reach that limit, obviously we overcame this situation long ago, and it's included in actually VMD. It's called the JS file format. It's documented online. I'm not going to go into details, but it can handle much larger systems. It also handles some other specialties. Like for instance, if when you're building a system that has, like say you're building a capsid drug system, then you have many copies of the drug. So you also have a limitation. Segments used to have a limitation. They can only contain, if I'm not mistaken, 10,000 atoms per segment. So you also run quickly out of segment names, and you run out. If you have a big system, you run out of these fields. So the new JS format allows you to have pretty much unlimited number of segments. But it doesn't have for instance, the PDB problem where you have the size or the memory size of the coordinates. It's fully compatible both NAMD and VMD, but that's only if you're interested in studying larger simulations. In any case, let's. I mean, I know you guys did some of these yesterday, but let's talk about a little bit again. So something that you want to do when you prepare your system is obviously add the solvation box, right? So you need to add the water surrounding the protein. So adding the water is not necessarily a trivial matter, as many of you would know. So many PDBs, if it is a high-resolution PDB, is going to come with some waters bound to it. It's also going to come with some other ions bound to it. So in general, you really want to keep those. So if it comes with any crystallographic waters, if it comes with any crystallographic ions, you want to stick to those, because those are usually structural waters, and they're going to affect the stability of the protein during the simulation. Then adding the bulk water, as some of you guys might have seen, is easier, because you can use something like the Solvate plugin or even the QuickMD plugin. The basic idea, we talked about a little bit about ensembles before. So how will you equilibrate? What is the normal practice to equilibrate a system where you actually just added a water box that what is the density of water? Right, and what is the water density? What is the density of water that was in that simulation box that you guys were doing yesterday? Did anyone check? So actually, the density of water, the density of that simulation box is a little bit lower than what it should be. And what do you think will happen? Let's suppose we have NVT, right? You have a constant volume. We run the simulation, but we're below of like liquid water density. What do you think will happen? That's if you have constant volume. You think the whole box is going to shrink, right? So your periodic cell will be out, and then the whole box shrinks. Everyone agrees? No? A wild guess. Well, this was a wild guess. We don't know if it's correct.
It's constant volume, it cannot shrink.
It cannot shrink. Oh, it can shrink. Yeah, you can just don't have contact. You just have the whole thing has the simulation box is constant, but not the solute. So now the water becomes the solute, which is what he's saying. So you have the water becomes compact. The simulation box the water becomes smaller than the simulation box. So what actually happens is you start seeing bubbles, right? You're going to have, water will try to stick together, but it's not going to shrink isotropically. You're going to start seeing these bubbles in the simulation. You're going to see empty space, like spheres of empty space, right? So that's because the water density is below what liquid water density is. So now what we normally do in our simulations is we first run a little bit of MVT with the protein restraint, and this is what we were talking before. You run a little restraint, you let it especially the water surrounding the protein to accommodate to the structure and not the other way around, right? So because you kind of put the water ad hoc, so you first let the water accommodate to the structure of the protein. But then you run MPT, and then you actually shrink the water box a little bit. And then you can run MVT, because you have to check that what you want to check is when you run the NPT, you look at the pressure, you can plot the pressure, and then you can plot the volume, and then you can see that the fluctuations of the pressure are very small, and you can see that the fluctuations of the volume are very small. Then you can turn off varostat. And then because the volume is more or less constant, so you're going to have less fluctuations of the pressure. And that way you can run an MVT for a production simulation. And you won't have these ugly, ugly vacuum of spheres. Yes?
Why is it then set up for something lower than that?
What is it lower?
Why
repeat the
can-
question?
What she is asking, why is the simulation, the water box that we provide with VMD set to a lower density than liquid water? So the reason is because if it was already too densely packed, it will actually, the equilibration process will be a lot slower. So by doing this, we're actually letting the outer parts of the system equilibrate by shrinking the size of the simulation box. And that actually the water starts moving. I don't know if you guys had a chance to look at the, did anyone run simulations yesterday or no? Okay, I should have shown that. But that's a situation there. So it becomes even more problematic when you have who has worked with a lipid membrane in a simulation? So you guys how do you guys normally generate the lipid membrane? Charm GUI, right?
Just use the VMD, the membrane builder.
The membrane builder. Charm GUI is better. But yeah, that's a pre-equilibrated membrane slab, right? And it has the lipid tails are melted and everything. It used to be back in the day you have to do all this by steps, and it was a lot of work. But if you wanna, yes.
I was just curious. You're saying that because I'm actually melting the lipids right now.
Yeah.
So you're saying that the charm GUI.
They give you a pre-melted, yeah.
Oh, okay.
Which is something, yes, saves you a lot of. So when you build, when you use the membrane builder in VMD, the lipid tails are straight, and so you need to melt them. With the melting meaning just like you have to let them reorganize. But the charm GUI has, yeah, pre-melted tails, and I think it's a pretty good protocol. In any case, you can actually use your charm GUI generated PSF PDB and run it on NAMD. So there is another interesting story I can tell you guys here. So typically, so I don't know how many of you guys work on ion channels, but maybe, yeah, I can tell you guys about that. So typically, if you want to have a gradient across the membrane, what you use is the E-field functionality in NAMD, which all it does is it adds an extra term to the potential, right? It is just for every atom is just adding a force which is Q times E, right? In the direction that you define in the configuration file. So that has worked for multiple years, and part of the limitation is because of periodic boundary conditions to avoid, like, obviously surface effects, but also because of the electrostatics. So recently, and it's available in NAMD, so if you want to do something more, like you actually have a gradient of ions across the membrane, not just you don't apply an electric field. There is the multi-level summation method. We can use, it's explained in the documentation. I don't think there is a tutorial yet. But with that one, you are not required to have periodic boundary conditions. So you can actually have a real gradient across a membrane. So typically, another way people accomplish this is by having two membranes and having the inner part between the two membranes and one potential, and the outer part of the PVC another potential. Now, with multi-level summation, you don't have to do that trick. You can just have a single lipid membrane, and you can actually have the different gradient directly on the membrane. And it's very simple to activate. You prepare your system as you always prepare it, and then you just tell NAMD not to use PME, but to use multi-level summation, and multi-level summation, and it just replaces the way the electrostatics are being calculated. It's as accurate, and the performance is the same. So that's something new that you guys might want to explore.
That's in 211?
That came out in, I think 210. I think since 210 is there, but it's definitely in 211.
What's it called again?
Multi-level summation, MSM.
And just to kind of back up a little bit,
Yeah.
if I turn on the Langevin thermostat, but don't turn on the Langevin pressure,
Mm-hmm.
does that mean I'm implicitly or automatically doing an NVT?
That's an NVT simulation,
And
yes.
then if I turn on the pressure, then I'm doing NVT.
MPT, that's correct, yes. And if both of them are off, then you're doing NE, yeah. NE. Oh, actually, if you have periodic boundary conditions, I guess they're technically in NV, right? Yeah. Yeah.
So are you
Yeah.
recommending the multi-level summation method for electrostatics for only for membranes or just?
Oh, you can. Okay, so it's general. You can use it for anything. So the main goal with multi-level summation is to completely replace particle mesh world. You can use it for anything, but this is like a straightforward application. Yeah, because it reduces the system size immediately. If you're having the, okay, first you don't have to use the artificial electric field, and second, if you want to make it more realistic, you don't have to have the two lipid membranes with the gradient across. Like you don't need two lipid membranes; you only need one. So it reduces the system size, which in turn help you with more sampling. Okay, so that's kind of like touching base on solvation and how to equilibrate a solvated system. I talked briefly about C ionized yesterday. I don't think anyone had a chance to play with it.
One question.
Yes.
Can you explain about the periodic boundary conditions?
Periodic boundary. Let me see if I have. If I'm going to talk about it later, maybe I can jump right now. I don't have anything. So what? I don't have slides for periodic. What exactly do you want to understand better? So why do you do periodic boundary, or?
Yeah, I want to understand how it represents the whole system ensemble, or ensemble. Does it represent the ensemble of molecules? Or?
So periodic boundary conditions represent. So you essentially have your simulation box, but then you replicate it in every dimension, right?
So what does it signify? Like, does it signify having many molecules in the system? Or?
You still only have. Well, I mean, yeah, it actually means you have multiple replicas. So like if your solute crosses and it interacts with the guy in the next periodic cell, they're effectively interacting. So you're, for every purpose, that replica exists in there. So there are interactions between, there are definitely interactions between first neighbors in the periodic cells. Is that what you're asking, or?
Yeah, I didn't understand why it has to be done.
Why it has to be done. So you can play with it. So one of them is to keep the constant volume, to enforce the volume. The other one is so the density, like, I don't know if there was, in the NAMD tutorial, the first part is a sphere, right? Right, and then you run that, but you have no, as far as I remember, oh no, there is pressure control on the radii. Yeah, the system size is also smaller than having the whole sphere. So part of the motivation was to reduce the system size versus having the entire sphere, right? Like you in the NAMD tutorial, you do this, like you have a single protein and then you have a sphere. So that sphere is much larger. The required radius of that sphere is much larger than if you have a single protein with periodic boundaries conditions. So it reduces the system size.
If we ignore the periodic boundary conditions, does it affect the calculations of the non-border interactions?
Of the non-bonded? Yes, because you have, well, yes, so you effectively will have edge effects, right? Like the water that is in the limit will be interacting with vacuum. Yeah, right? There'll be vacuum at the edges.
That's why you use periodic boundary conditions in statistical mechanics, is to avoid the effects of edges. So you've created an artificial edge which will itself affect the system.
So, but in the case of this membrane, suppose if we consider a periodic boundary condition, it will be like having many membranes, many cell membranes, right?
On the XY plane?
Yeah.
Uh-huh.
So, if you are studying an ion channel movement of some solutes through the membrane, how does it affect the reality? On the other side, you have the same membrane.
Oh, yeah, that's why people okay, I now understand. So that's why people, yeah, so like you will expect to have a gradient across the membrane, but what you're saying is like this solvent is the same as this solvent up here, right? Yeah, so that's the issue. Like if you create a gradient here, you're automatically creating it here, right? So there are multiple solutions to that. One is if you want to create the gradient, you apply an electric field. The other solution, which is doubling the system size, is you essentially have the mirror of this image down here, right? So you have the center, you have a central solvent, and then this exterior solvent. And then you get, that's what most people who are interested in translocation through a protein pore or a gate, that's what normally they do, is they have this mirror system, kind of like a periplasm, and then the periodic boundary condition. Now, what he's saying, and it's something that no one raised a question, is how will you do statistical mechanics on this system? Statistical mechanics is usually done on systems of infinite size. So what are you talking about? I mean, we've been briefly touching, we talk about ensembles in a finite system. So if you go and look your statistical mechanics book, anything that has finite size is an advanced topic, right? So finite systems are very particular systems, and that's also what you use periodic boundary conditions is. So like statistical mechanics is well defined. So in principle, it resembles an infinite size system, right? But actually we're still dealing with a finite size system, and it still has some intricacies that because we're having a limited number of particles, and that's maybe we'll touch based on that later if we have time. But that's right. And formally, like from the formulation of statistical mechanics, all the formulation is done with you assume an infinite size system. So there is that's what also periodic boundary conditions help you with. But when are you interested in the statistical mechanics is when you want to get quantify some physical property or some characteristic of the system. But if you're doing a mechanistic study, like translocation of an ion, people won't really bother if you have, they will bother you, but not too much if you have a system that is large enough so you can have the edge effects or move away from the area of interest. I don't know if there are any other questions regarding. Oh, sorry.
So if you were to run a lipid bilayer in a system like this without periodic boundary conditions, how would you properly account for the edges of the bilayer? Because you wouldn't want them to be exposed to vacuum. Yeah, you wouldn't want them to be exposed to water really either.
Well, actually, we've done those experiments. They actually close. The head groups reorient and make this nicely curved. On the edges, yeah, it curves. Yeah, so many, but that's only for embedded proteins. So maybe I'll show you guys. This was a coarse grain simulation of an nanodisk assembly. But I mean, obviously, this one has the scaffolding proteins at the edges. Oh, that one doesn't have the movie. Oh, I was hoping it had the movie. Oh, it doesn't have the movie. Oh, it does. Oh yeah, there it is. So you can see how the first thing they make is a vesicle, or not a vesicle, a micelle, right? So when you have a flat surface, they kind of like do the same, like they curve at the end and make a nicely looking slab of membrane. It takes a while, but that's what it does.
Okay, because I do self-assembling as well, and I'm trying to think of how this would end up applying to my.
Yeah. So if you're yeah. So on the XY, as long as I know, as if we're interested in the protein, we always do periodic boundary at least on XY on the plane of the membrane. But there are some studies, people in the lab are interested in looking at how some proteins induce curvature. So then, because you have an infinitely large patch of membrane, it makes it stiffer, the curve. So that's when they start using these little patches of membrane. Also, I don't know if it's in these slides. You get it here. I think it's here. Okay, well, while this loads, so yesterday I showed you guys the chromatophore patch, which is effectively contains a lot of lipids. And if you remember, that one also had the open, it was not a periodic slab. It had water on the edges. And what we observe, even at that scale, that's a 20 million atom simulation, what you still observe is that the head groups rearrange and make these nicely curved edges.
So it doesn't really affect the result that you were hoping.
If your protein is far from the edges, it shouldn't affect it.
But for a small system.
Yeah, for a small system, definitely. I mean, yeah, you're right there at the boundary, right? Well, if it loads later. I wanted to talk. Oh, sheesh. I wanted to talk about, switch topics a little bit because we haven't talked much about a lot of things, but obviously we tried to cover a lot of material. So I guess everyone here is familiar with ubiquitin. There's a pretty well-studied protein. The name comes because it's quite ubiquitous. It's involved in the proteasome degradation. You know, like when a protein is being tagged for proteasome degradation, it gets this polyubiquitin tails. But we're not going to look into that. Let's look at something more simple. Let's suppose you just get your high resolution ubiquitin simulation, a structure, and then you run an MD simulation. So if you look at the NMR structures, of ubiquitin, what you're going to see is, because of the inherent flexibility of ubiquitin, you're going to see all these the overlap of the ensemble of structures. I apologize for the quality of the figure. It doesn't look too good, but you can't believe me that this is an ensemble of structures that the NMR is observing. So when then you start running a simulation, you pick one of these, then you start time zero, and then you calculate you calculate over time the root mean square deviations, is measured in Armstrongs. You can see how the RMSD quickly changes, and then it reaches this plateau. So I guess, is everyone familiar with the definition of the root mean square deviation? It's a very simple calculation. It's just simply the square deviations between.
Different forms of it in NAMD.
Say what?
I mean, there's a couple forms of RMSD that are used in NAMD, some with optimal rotation.
So, okay, so we can talk about that. But so the most naive definition of RMSD is that the direct differences between the coordinates. Now, as you're pointing out, this definition doesn't consider any alignment between your states, right? So you can have, just a simple example, you can have your protein just being translated by a fixed amount, and if you calculate the RMSD, it's going to be gigantic. He's not going, I mean, if you just use this equation, it's going to get a large number just because of that translation, right? So what you want to, what you effectively want to do is eliminate the rotation and translation degrees of freedom, and that's how you can actually define a proper RMSD. Now, there are multiple ways of doing that. There is the CAPSH method that was published in the 70s. The CAPSH method is simply like you actually do the cross correlation between the coordinates. You effectively calculate the dot product of the two coordinates, and then you just do an SVD. And the first eigenvalue is actually is the minimal. You don't even the only requirement is that any translational motions have been removed. So the CAPSH method can actually give you without calculating the rotation matrix, it can give you the maximal distance between the two data sets. And it's simply like a dot product between the coordinates that you want to calculate and then doing an SVD of that correlation matrix. And the first eigenvalue gives you the RMSD without having to calculate the rotation matrix, which is, I guess, what you're referring to. Yeah, I mean, if you have to calculate multiple of these, you want to do it quickly, so you use CAPSH. There is also another method called QCP, which is based on quaternions. And that one's a lot faster. And as a matter of fact, when we were touching base on clustering, an easy way to do clustering is to calculate RMSD, right? So suppose you have 1,000 time frames, like you have 1,000 structures, right? If you're calculating these 1,000 frames from a reference, that's telling you nothing about neighboring structures, right? Like, so every point on this plot represents a structure, but this plot is telling a lot of information with reference to the initial structure, but it doesn't give us any information regarding neighboring structures. So a way to do cluster is to actually build. I don't have one figure, but what you do is effectively you calculate the distance between every two structures in the simulation. You calculate RMSD, so you effectively had a heat map, a contact map in RMSD space. So when you actually look at that, you start seeing, well, if anyone is interested, I can show you what it looks like. I can look for papers, but it looks like you have these. So if you have like a heat map, you will have these regions where things are really like very, very close to each other. You have these other regions that are really close to each other. So you can actually start clustering structures in this space. But in that event, you're actually calculating number of structure square over 2 number of RMSD calculations. And that's when you actually are interested in doing some of this CAPSH or QCP, because this is actually, this is not, when you calculating the contact map for a trajectory is actually n cubed. So like the complexity is n cubed because number of, actually it's not even n cubed, it's n time, it's n, so like the length of the trajectory square times the number of atoms. That's the complexity of that calculation. So if you have a very large system, you can actually, if the number of atoms of actually degrees of freedom is similar to the number of frames, it can become a cubic problem. So that's when you start looking into more, like I mean, we use high performance, we use supercomputers to kind of get these contact maps and do the clustering. So, but I mean, if someone is more interested in that, we can talk more in detail. But it's a very, I mean, RMSD, as simple as it is, it already poses a lot of complexities just by removing the rotations and translations from the calculation. But I think the message here is that when you run your simulation and because of the internal fluctuations, like we already know that the proteins are not bricks, they're not, I mean, they crystallize, but they're not really rigid. So you just because you see a slight change on the RMSD, just because you see fluctuation of the atoms, doesn't mean your simulation is wrong. Now, if you see like it's unfolding and doing crazy things, then you have to be a little bit more careful.
So you have the reference molecule is the first frame?
For this plot, yes, because so RMSD 0, yeah. So the reference is the first frame, but you can pick. It's an arbitrary choose, right? So actually, we're trying to move away from this picture of assessing the structural stability, because it doesn't tell you. I mean, RMSD is really good when it's small, because if it's small, it tells you okay they're similar. But if they're different, like it's a large number, it doesn't tell you anything, right? So we're trying to move away from this picture, and we're working on that. So maybe in the future. Yes.
If I'm comparing two systems, A and B, does it really, like, if there is lower RMSD, it's more stable than the system with higher RMSD?
Say it again.
So does, like, if a system has a lower RMSD compared to other, does it really has to be like it's more stable compared to other?
So it really depends how you define stability. It probably is telling you it's more rigid, but I don't think I mean, if the system itself is.
Like the flexibility is.
So flexibility, that's usually calculated using RMSF, right? So, but this is actually RMSD here. But RMSF, the root mean square fluctuations, right? So you're actually measuring you're adding quadratically the fluctuations around equilibrium. So RMSF actually can tell you something about the flexibility, at least the local flexibility, yeah.
So for RMSD, we basically look at the trend, the plateau is required.
Yes, that's the common practice right now, that you reach this plateau. Now, the amplitude of the like this number, is it's really arbitrary, yeah.
But you don't want it to be too large.
Well, if it's 12, yes. If it is 6, so if it is, yeah, but there is still debate what is a good number here.
I think I had seen in one video that Schulten had mentioned that up to about an angstrom, that represents more the thermal fluctuation than any real.
Well, but it also depends what you're measuring here. Like, I mean.
What from what initial structure?
Well, not only that, but what parts of the protein are you including in the calculation, right? Yeah, because I mean, if you're including the loops are inherently flexible, so they can exhibit fluctuations that are pretty big. So there is some. I mean, in general, you can, if it's 1.5 is really good. That's pretty good. But if you go to 3, that's still okay. It's within what people will accept. If it goes 5, 6, you need to start looking into maybe some local unfolding. But this is not the ultimate measure. I mean, you should definitely like. For instance, we saw yesterday how you can look in timeline how the secondary structure is maintained, right? So that's another check. Like you can see like, oh, this is not like this helix is unfolding here. That's a more realistic check than RMSD doesn't tell you much. It tells you kind of a first steps, but it tells you some about the inherent flexibility of the proteins. Do you have a question? The potential. The potential. Let's do a little trick. Let's do a game here. So, how do you think? Okay, so we already talked about our potential, right? How do you think each of these terms depend on temperature? How do you think the kinetic energy is going to depend on temperature? Sorry? The kinetic energy? So like, say like, is it going to be, so because, okay, so this is the kinetic energy, right? So if we increase the temperature, the velocities are going to increase. So are we expecting the kinetic energy to go quadratically, exponentially? So if we increase the temperature, then we're going to see an increase, exponential increase on the energy.
If you look at it
That's correct. How about this term here? So the kinetic energy, okay, yeah, it's a equipartition theorem. It should be linear. That's it, right? How about this term here? How about this term here? This one, we don't know, right? That's not quadratic. As long as it's quadratic, we can say that the energy depends linearly with the temperature. So if this is just like for curiosity, if you want to see how the energy varies with temperature, like as you guys correctly predicted, the kinetic energy plotting black here scales linearly with the temperature, right? So does the bonded energies, and so do the bond length, and so do the angle terms. The dihedrals we don't even show here, but the van der Waals seems it doesn't even depend on the temperature. And this guy seems to be kind of fluctuating, doesn't really have a strong relationship with the temperature. So let's see if we can get to what you were asking before, which, oh, geez, I don't have it here. I thought I had it. Oh.
Right, yeah. I have to think about what that's not these temperatures. You have to go to much higher temperature.
Here, let's look at this one here. So you were asking if the potential energy, if you have a minimal potential energy, if it is a more stable structure, is that what you were asking?
I think that's a good measurement of whether you have a stable structure.
Okay. So if you actually look at the kinetic, so what is going to be the total energy of the system? It's going to be the kinetic plus the potential, right? There is energy conservation. Let's say we're talking NE. So actually, if you look at if you plot kinetic energy, you're going to see these fluctuations, right? So why do you think? We're doing NVE. So what is? We're doing NE in this case. Why is the kinetic energy fluctuating? What is that energy going? It's in the potential energy, right? Like there is an interplay between the potential and the kinetic. So actually, with that's telling you is like your potential energy is not really telling you the whole picture just because you have a global. It's probably not even a global. Just because you have a local minimum, the potential energy doesn't mean that the system is going to be more stable once you increase the temperature. So to answer your question, it's a good starting point for a simulation. Just because it is you have two structures. One has a lower potential energy. Doesn't necessarily mean it's a good structure. It means it probably has less problems than the other structure. Let's do. Let's finish with a few. I know people talk about the coarse grain a lot. I've been asking. So a way of coarse graining is like you have the shape-based coarse grain. We have a tutorial if you guys want to work on it, but there's also the residue-based coarse grain model. So in the residue-based coarse grain model, you're essentially reducing groups of atoms. For instance, a benzene is reduced to 3 particles, or you can reduce like the lipids to a finite number of atoms. The most used, I don't know how many people have used the Martini force field. Yeah, the most widely used. Have you used it for proteins?
Yes, yeah,
then how do you still apply ENM, elastic network models?
Yes.
You're still right. So the problem with Martini is like the proteins, otherwise the protein just becomes unstable, right? So a problem with the Martini force field is because you have such coarse representation, you actually introduce what is an elastic network model, which is you artificially add springs based on the shape of the protein. So it's a mixed model. So, I mean, obviously you sample larger time scales, but you have to be, I mean, you also have to, when you do the interpretation, you have to be careful with what you do. Martini is fully supported in, do you guys run it on NAMD or GROMAX? GROMAX, right. Yeah, it also runs on NAMD. We also have the pace force field, which is, okay. Oh, okay. Yeah, but right now there is, so even the charm GUI, you can prepare your Martini, and also there's the pace builder in charm GUI, and also generates the NAMD files for use with the pace force field. So yeah, obviously, I mean, as we were discussing, like coarse grain has its flaws, like for instance, structural stability is compromised, but you can also sample longer timescales. So as long as you know that you're compromised in accuracy for time, that's okay. I think I already showed this one. So this is the other extreme of coarse graining. This is what is called a shape-based coarse grain. So this is an entire virus capsid, and like what I showed before is like you coarse grain every residue in like you go do a mapping from like a residue still represented by maybe 3-4 particles. This is like really extreme because like entire parts of the protein are actually sampled to a single ball, a single bit or particle. So for instance, here you get a single bit for this part, a bit for this part, and so on. So this is what we refer as the shape-based coarse grain. Is also very powerful. There is a tutorial if you guys are interested. You can also follow it. So what is, obviously you're sacrificing a lot of detail, but you can also do interesting experiments. So yesterday we talked about the AFM of pulling a single protein. Here we're actually looking at, this is an STMV capsid, and this is an AFM, the tip of the cantilever, and we're looking at how when you do these nano indentations of the capsid, how the overall morphology is changing. And this is one of the advantages with a coarse grain, right? Like you can explore these. This is a gigantic system, and also like you're actually looking at very long timescales, like the microsecond. So like, obviously, if you're careful enough, you can get some interesting results from this. But you also like, this is a very, very, very coarse representation of the system. It's possible in NAMD. It's relatively easy to do. So if you guys are interested, there is, as I mentioned before, there is also a coarse grain. But how accurate it is, actually it was hepatitis HBV. How accurate it is, so you can see that you have the experiment here in gray, you have the simulation in green. So you can see the nano indentation, which is measured as like how much the tip is pushing versus the force, and you can see there's a pretty good correlation between the two measurements. So if you're interested in looking, for instance, at the nano indentation, if in virus capsids there has been this debate whether, like, I mean, if the virus capsids are made of essentially hexamers and pentamers, there has been a debate whether the pentamers or the hexamers are more rigid. And the way people have been studying this is through AFM nano indentation. So, but they just press, they don't really know where they're pressing. But now when they compare to like the simulations, they could actually see that the pentamers are more rigid, but they're also more brittle. So this is, I mean, again, this goes to the beginning of what we were discussing at the beginning of this session, which is as long as you have a scientific question, you have an arsenal of tools you can use to answer and explore. Yeah, this is a very, very coarse very coarse grain. I don't know if there are any questions up to here. I think we're running out of time. Okay. Let's. I'll show you guys one. I think we're due for lunch, but I'm going to show you one last example of that I really like of the coarse grain. The movie looks a little bad, but this is the formation of this, the tubulation of these bar domains. So like it's a bar domain sculpting. This is also coarse grain, but it's I think it's very nice how you can actually see tubulation of a system of this size. And if you look at the time scales, it's also very, very ambitious. And it's very nice because it matches cryo-EM data. So this was actually published before the cryo-EM data came out, how the bar domains actually do this tubulation of the membranes. So this is a membrane and the bar domain system. Obviously, it's the level of coarse graining is a shape-based coarse graining, but this is also within the limits of what NAMD can do and what you guys can do, anyone can do really. And okay, I think that's enough for right now. If you guys have any questions, I'll be around for a couple of hours. I'll upload the slides and for any references if anyone has any question at this point, or we can talk about it later. Nope. Okay. Thank you.